Welcome to the MIA Part 2 module on Advanced Hodograph Interpretation. I'm Pete Wolf, the Science and Operations Officer at the Jacksonville Forecast Office. The objectives of this module are to review the basics on hodographs, understand what changing the hodograph length and concavities mean with regard to pressure perturbations and how this can affect convective storm structure, mode, and intensity. Understand how the changing hodograph shape and changing storm motion vector can affect the pattern of storm relative flow vectors and why this can influence storm structure, mode, and intensity. And to interpret how small-scale environment changes can affect the hodograph, and thus how small errors can affect accurate environment interpretation. This module focuses on the application of the hodograph in operations. To understand the why and the how regarding this, you'll be asked to complete 4 additional sub-module videos in YouTube that are related to this one. These represent segments from a presentation from Dr. Ariel Cohen. The combination of all of these plus this module will probably require about 2 hours to complete, but it's important not to shortchange this within a shorter module. So complete the full module as it is set up. When you reach a sub-module video, you'll enter the link URL in a different browser to view that YouTube video, then return to this presentation. So a key point with regard to the motivation for this module is that this is one of the most valuable tools for the meteorologist to understand what is going on through the troposphere and what is likely to influence sensible weather. This concept of the vertical wind profile and how it appears on the hodograph. Why is this important? Because there's no coincidence with the wind. Patterns of wind and shear and changes to those patterns in time and space mean something. Something is occurring in the troposphere that could influence convection. Here we see an example from a long ago wind profiler, when we had wind profilers, showing how quickly environment can change in time and space. You see somewhat different changes in the pattern of speed and directional shear hour by hour. Here we have another example. This one shows a frontal surface moving across the area, and we see the slope of the front and the deepening of cold air behind it hour by hour. We also see the change in the vertical wind shear hour by hour ahead of the approaching front. So vertical wind profiles and hodographs tell us a lot about how the structure of vertical shear is changing, even as quickly as hour to hour. Here again we see the frontal boundary. We also see some wind maximums as well that may reflect weak waves, even shallow ones, in the lower atmosphere. True or false? An image of 0 to 3 kilometer storm relative helicity gives us a full picture of the level of streamwise vorticity that could be ingested into a developing thunderstorm updraft. I hope you answered this false, because it is false. It's only close to accurate for a right deviating storm motion and accurate hodograph length and shape. The SRH value that you see on these plots is usually not valid for initial storm development that is not turned to the right. And it's also not valid for a left deviating storm, or in situations when the hodograph contains error. So even small changes to the hodograph or to the storm motion vector used can lead to substantial changes to SRH. A key point is that because of the variable hodograph displays that relate to a given level of shear or SRH in a plan view plot, it's important not to just focus on that number. Look at the hodograph to see what the number means for a given time and location. So here we see an example with 0 to 3 kilometer SRH, and we have X marked where we have a value of 250. But what does that mean? It can mean a variety of things. It can mean a variety of different hodograph shapes. Here are 4 examples of hodographs and storm motion vectors that give us about 250 for SRH. But as you see, they can mean very different end results. The upper left probably favorable for a tornadic storm. The upper right is likely not favorable given very weak storm relative flow where we have that loop in the hodograph in the inflow layer. The lower right actually may favor a left moving storm over a right mover, and so forth. So you have to look at the hodograph and see the actual shape and the concavities that represent vertical shear in the atmosphere. So never trust a single value alone. And again, this value is based on a 25 to 30 knot easterly wind, as you see in the vectors. That's for a right-moving storm. That's not for the initial storm motion. So also never assume a value of SRH is based on the exact storm motion vector. Changing motion vectors can change things like SRH as well as storm relative flow vectors. In this example, we see 3 hodographs all producing a 0 to 3 kilometer SRH of 250, but with different motion vectors giving us a different pattern of storm relative flow. The left hodograph represents pretty strong storm relative flow aloft to distribute precipitation down shear away from the updraft, whereas the right hodograph shows much weaker storm relative flow aloft that might keep the precipitation within or very close to the updraft core. So hodographs are a very important tool for the mesoanalyst for understanding how shear is changing in time and space. It helps us understand not only the pattern of shear, but also the pattern of storm relative flow with height. So each shear vector, such as in the orange example, basically connects the ends of the tops of 2 wind vectors, representing the bottom and top of a given layer. The lowest 3 kilometers, the inflow layer, if you will, is shown in red. And so given the storm motion vector to the right moving storm, the green arrows represent storm relative flow within the inflow layer, or storm relative inflow. Whereas the blue arrows represent storm relative flow further aloft. How is it going to distribute precipitation further aloft relative to the updraft core? So a key point is that some environment changes and what they represent can appear more clearly on the hodograph than they can on the vertical wind profile. And I'm going to show you some examples. Take a look at this vertical wind profile. Would you say that's a favorable profile for tornadoes? After all, we have a strong veering of wind and an increase in wind with height overall, pretty strong shear both in terms of direction and height. However, believe it or not, this is not a favorable profile for tornadoes. And there's a key reason why, which is very subtle on the vertical wind profile, but it sticks out on the hodograph. And we see this loop in the upper part of the inflow layer, the loop in the hodograph, right near where the storm motion vector is, meaning you have almost no storm relative flow through that particular part of the inflow layer. You're not going to be able to move precipitation down shear. It's going to build up in the updraft. Hard to get a rapidly intensifying updraft to support vortex stretching and acceleration when you have a lot of precipitation stuck within the updraft core. This is an example where you may end up getting a core of up to maybe 20, 25,000 feet, where normally you would expect a core up to 35, 40,000 feet because of the precipitation within the updraft. This is a less favorable hodograph for tornadoes compared to one that does not have that loop, that small area of weakening winds in the top part of the inflow layer. You can't see that very easily on the vertical wind profile. How about this wind profile? Is it favorable for tornadoes? Again, you have some veering of wind at low levels and pretty strong speed shear with height. However, if you look at this in the hodograph, you get this. You get an opposite curvature of the hodograph in the inflow layer that actually would be more supportive of the left mover. Might be more favorable for very large hail and not for a longer tracked right mover with a tornado threat. So you have to look at the hodograph, not just the wind profile alone. It's much easier to see these changes in shear on the hodograph than just simply looking at the vertical wind profile. So the mesoanalyst needs to be focused on the hodograph and hodograph changes in time and space, which can be substantial, as much as for any other tool. So lack of or improper use of the hodograph, just as with the skew T, can lead to erroneous environment conclusions from the mesoanalyst. This is a fascinating radar animation, and what it illustrates is rapid environment change in time and space, leading to different end results. We have a forward propagating MCS across Oklahoma and eastern Texas. We have back building convection early on in Arkansas. We have training convection that sets up after the MCS in south central Oklahoma late in this animation. Just a variety of different things occurring based on different types of environments. So initially when you have a storm develop, and let's say you have a hodograph that looks like this, it's a pretty straight line, the motion vector initially will be very close to or on the hodograph. And that means you don't have a lot of streamwise vorticity. All the storm relative flow vectors are basically almost parallel with each other with height, basically pointing towards the southwest down low and towards the north and northeast up high. The end result of this is if you had a football flying through this environment, instead of spiraling, it would move like this. This is referred to as crosswise vorticity. And when this is ingested into an updraft core, the rotation is not co-located with the core of the updraft, but rather located on the edges of the updraft. And you can get rotational signatures, but they're not co-located with the updraft, where you would have the stretching of the vortex, as you will. For that, we need streamwise vorticity. So if the motion vector instead of at A was actually at B, off the hodograph curve, then we have a varying pattern of storm relative flow vectors. And in this environment, the football would spiral. And as it gets ingested into the updraft, that rotation would be co-located with the core of the updraft. Now we're in for business as far as a tornado. We have the rotation co-located with the updraft that can then allow for vortex stretching as the updraft accelerates. Okay, it's time to pause this video and view the first submodule video from Dr. Ariel Cohen. To access this, you're going to need to utilize this URL, type it into a browser, and then play the YouTube video. When you're done, you come back and continue this one. Thank you. All right, hopefully you reviewed Dr. Ariel Cohen's first video and are ready to continue. You might want to take a short break if you haven't already before continuing on in this module. Okay, so let's talk about the impact of hodograph length. That length for a given layer is related to the strength of the vertical shear through that layer. So in this example, the red hodograph represents vertical shear of just about 20 knots, whereas the blue hodograph represents 70 knots of shear through that layer. The length of the hodograph is more relevant for convective mode than just the strength of the wind. This is why along the east coast of Florida, for example, on a hot summer day with mid-level flow only around 20 to 25 knots, onshore flow on the east side of a sea breeze boundary can locally increase hodograph length to represent 30 to 40 knots of vertical shear through the layer, even though wind speeds throughout the layer are 25 knots or less, as you see in this example. This can lead to supercells with hail and even brief tornadoes in what appears to be a weak flow environment, but it's not a weak shear one. So here's an example on a day that we saw supercells develop on the east side of sea breeze, where we had enhanced onshore flow beneath moderate mid-level flow. On the right, we have three HRRR 1 hour forecast hodographs from locations from central South Carolina at the top, working southward to east central Georgia at the bottom for the same day and time. Note the difference in each hodograph shape. These changes in shape, be it due to small changes in wind direction or speed within shallow layers, or larger changes through a deeper layer, means something in terms of what's happening in the troposphere. They also influence the pattern of storm relative flow vectors and how precipitation is distributed for a given storm or system. Changing the hodograph shape, particularly by adding inflections and different concavities, can affect the generation of perturbation pressure gradients, as well as patterns of crosswise or streamwise vorticity. It's time to look at the second video from Dr. Ariel Cohen. So here's the URL to put into a browser and view this one. And then you can pause the video you're watching now and then return to it when you're done with Dr. Cohen's video. Thank you. Okay, you have completed Dr. Cohen's second video. His third video is coming up next, so you might want to take a short break before continuing. So on to the third video that deals with linear effects. Here's the URL again, copy that or type that into your browser, and when you've completed that video, then come back to this one. Thanks. Okay, maybe time for another quick break before we continue. So now let's talk about the impact of changing storm relative flow. When you have different hodograph curvature and length, you can get different patterns of storm relative flow vectors with height, and that can influence precipitation distribution within a particular convective storm. The top image here shows an example with weak mid-level storm relative flow, but strong upper-level storm relative flow. The middle example shows strong storm relative flow at all levels, which we typically see with a long clockwise curved hodograph. While the bottom image shows a different hodograph configuration with strong low and upper level storm relative flow, but very weak mid-level flow in this example. Each of these hodograph shapes means something different in terms of storm structure and precipitation orientation. As a mesoanalyst, it's important to try to be able to decipher this and understand how storms are going to develop on radar before radar shows its hand. So a key point is that, as with other environment factors, vertical wind profiles can change considerably and rapidly in time and space, which can mean sharp and rapid changes to the hodograph, and it's important to pay attention to these changes. Here we have different wind profiles here going from south to north across the central part of Georgia for the same hour of the same day. You don't see a lot of significant differences in the hodographs, some changes in how much directional shear there might be, but they all show very strong speed shear. However, they do lead to very different shapes in the hodograph, different concavities. Some show favorable shapes for tornadoes, others show issues such as loops in the hodograph. You see, for example, the lower left having a loop within the inflow layer, which could have a different impact on the storm than having that loop further up in the upper part of the storm structure on the upper top image. So different shapes, different concavities can mean different end results. These changes are not coincidental. They mean something is going on in the troposphere. Okay, we've reached the final video from Dr. Cohen. So enter this URL in your browser and view that video, and then return to this presentation to continue. Thanks. Okay, time for another break. This is a fairly lengthy module, but it has a lot of very important information. It's important to take breaks from time to time, so take one here before completing the rest of the module. Now we're going to look at a case example to illustrate what we've covered. And this will be a late night case from November 30th of 2020. We have a strong upper trough that's moving quickly northeast across the southeastern United States. We have a north to south band of discrete storms and short segments that was forecast by the CAM models to develop, given a substantial angle of the deep layer shear vector to the surface trough in the band of storms. The high-res NAM revealed a low cape, high shear environment, typical across southern Georgia and northern Florida in the cool season. Despite SRH values above 300 meters squared per second squared, the model showed very weak updraft helicity tracks, with stronger ones off the southeastern North Carolina coast, primarily during the 6 to 12Z period, as you see here.